Good morning to everybody. Let us continue with our postgraduate course on advanced hydraulics. So, we are still in the first module and it is the 8th lecture of the series. In the last class, we have described about momentum equation, energy equation, specific force. The quiz related to those portions are pending, and today first we will conduct the quiz of that, then we will go into the next part of the lecture. The first question for the quiz of last class topic: give examples of the local phenomena where state of flow changes from subcritical to supercritical or vice versa. Give examples of some of the local phenomena in open channel flows where the state of flow changes from subcritical to supercritical and vice versa. So, you just give some of the examples, you are aware of them. The second question suggests that if there is a reach of open channel, and two sections 1 and 2 are considered. If y1 is the depth here, v1 is the average velocity across the cross section at section 1, v2 is the average velocity at the cross section in section 2, and depth of flow is y2 here. If these are the given conditions in an open channel flow for a steady state prismatic channel, in a steady state prismatic flow channel, can you express discharge now here in terms of average parameters? The first question is actually whether can you express discharge in terms of average parameters. If it is possible, then state them. Third question: what is specific force? State the assumptions involved in developing specific force concept. So, these three are the questions for today's quiz. You answer them. It will take hardly 3 to 4 minutes to solve the questions here. Okay, let us continue with our lecture now. So, last class, as we mentioned, we have discussed on specific force. We have developed specific force from the momentum equation using certain assumptions which you have right now solved in your question. So, specific force was defined as say F is equal to q squared by G A plus h bar into A. If you recall them, say for any arbitrary cross section, the cross sectional area of flow is A, and if the centroid of this area, if it is at a depth h bar from the top surface of flow, then we are using them here to compute the specific force. Q is the discharge, G acceleration due to gravity, A is the area of the cross section. So, we have also suggested what are these two terms. The first term is nothing but the momentum of flow, passing through the channel section per unit time per unit weight. The second term is nothing but it is the force per unit specific weight of water. So, as all of these are related to some force per unit weight of water, even the left hand side F, it is also a certain quantity of force related to unit of water. The summation of these two quantities are therefore called specific force, and we are applying them in many of the open channel computations. We also suggested that in a small reach of the channel, where the slope of the channel is negligible, friction force can be neglected in a small reach. In such a situation, the specific force in two sections F 1 will be equal to F 2. This was also derived in the last class. So, what do you understand? What is the peculiarity of specific force? Why it will be useful? Again, let me write the same equation, F is equal to q squared by G A plus h bar A. Using this equation, now definitely you can plot specific force versus depth of flow, right? You can easily plot specific force. Say if this is the cross section of the channel, I can plot now specific force versus depth of flow easily. That is quite possible. You use this equation. Once you use this equation, it was observed that the curve was having some shape of this form. We will come into that, we will discuss more on that. If you recall your energy equation, for the same channel cross section, if you plot E versus Y, you had observed them that say you got something of this nature, the energy versus depth flow equation, you had got something of this nature earlier. So, if this is the depth of flow given to you, say y, if this is the depth of flow y given to you, then this is the initial depth and the corresponding at the same energy, the corresponding alternate depth will be somewhere here. See, if you call this as y 1, the alternate depth will be somewhere here, y 2. These things are already mentioned, you are quite familiar with these things now. In this case, however, if you look into the problem now, say in this cross section, if the depth of or from the top surface, the height at which the centroid of the area is located, if h bar, if it is at this place, and if you try to interpret the things now, say in the specific force curve, this also I can now make it into two portions, say A B and B C. I can just readily make this curve, means we can divide this curve into two portions, A B and B C, where from B C means that the direction of the curve changes at B C, that is what we want to mean it here. So, from these two limbs, initially when the depth of flow is y 1, that y 1 we can easily represent in the specific force versus depth curve y 1, same as well, right. It has similarly in the energy curve for the same specific force curve, there are two depths of flow. For the same specific force curve, say F 1, it has two depths of flow. So, let me give this as y 1 f and y 2 f. When you study hydraulic jump and all, where the local phenomena occurs, at those situations you will come into use of these two depths where the specific force are equal. Those things we are taking into account now. We will discuss those things later. So, these two depths y 1 f and y 2 f, if y 1 and y 2 in the energy equation curve, energy versus depth equation curve, if they were called as alternate depths, this we can call as sequent depths. If you see, this y 2 f is not at same height as y 2 in the energy curve, there may be slight difference that shows, or if you just extrapolate it here, the critical depth will be same, that we will discuss again. Here this thing, if you extrapolate it here, the energy location is somewhere here and there is a loss of energy. Here this was E 1 and this has now become E 2. There is a loss of energy when the flow occurs. So, there the depth will change from y 2 f, or so y, if it was at subcritical depth of y 1, then it may go to a supercritical depth of y 2 f rather than y 2 in some of the local phenomena. We will see them in the next modules, whichever deal with the local phenomena. So, let us discuss on this curve now again. So, you have this equation. So, you have plotted this equation y versus f using the same equation, this thing we have plotted them. You have observed the corresponding curvature. The location of the minimum specific force, see the minimum specific force, where it is. You just try to observe them. So, minimum specific force, if you try to obtain from this curve. So, this will be d by dy of q squared by g a right. So, this quantity should be 0. so that the force is minimum, specific force is minimum. How will you identify that now here? What is dy by dy of q squared by g a? You know a is function of y. Similarly, h bar and a both are functions of y. So, we will be dividing them appropriately. This is equal to q squared by g a squared minus q squared by g a squared d a by dy plus dy by dy of h bar a is equal to 0. Let us interpret it in this way. From this equation, how will you compute d by dy of h bar a? Look at into this curve, you know the depth of the centroid from the top surface, this is h bar. So, if there is a slight increase, say if there is a slight change in area, say this depth of flow is now changed, this quantity is dy. Let me suggest that this small change in depth of flow is dy. Of course, you know this is the top width at the top. Due to this change in dy, how this quantity h bar a will be affected? That is the thing you need to compute. Going through the picture, now I can suggest that for any small increment in dy, the increment or change in h bar a, it can be given as d h bar a. Okay? D of h bar a due to a small increment in dy, this can be given as the actual area. Now, h bar plus dy plus, I will write it again, a into h bar plus dy plus the change in area, how it got affected, t by 2 dy whole squared minus h bar a. This is nothing but, this was the original area, h bar, that the centroid, you are multiplying with the depth of the centroid into the area, that quantity earlier, and the quantity that is occurred by the small increment in depth dy, that is this quantity. So, from here, suppose if it can be approximated that this quantity, if it is almost negligible, if this quantity, if it is almost negligible, if it can be approximated, then you can suggest that d of h bar a is equal to a of h bar plus dy minus a into h bar, or this is equal to a dy. So, this is actually an approximation, d of h bar a can be approximated as a into dy. Substitute those quantities here, you will see that here if you substitute them, you will see that this is this quantity, you know, it is the top width t, as is evident, and as well as we have discussed that d a by dy is the top width T in one of our earlier lectures also. So, you will get this quantity as q squared by g a square T is equal to A. This is A dy by dy A, or you can suggest that q square T by g a cube is equal to 1. If you recall your energy depth relationship, the same relationship was observed. That is, this relationship q square T by g a cube is equal to 1 will occur only in critical flow conditions. Okay? So, what does this imply? If you compute minimum specific energy, at the minimum specific energy, it will give you the critical flow of the section. That is what it is implied. So, as the minimum specific energy also yields gives the critical flow, similarly, the minimum specific force also gives you the critical flow. So, next topic of ours is computation of critical flow. So, just recall the earlier portions of our lectures. How the critical flow occurs, or what are the properties in critical flow? If you have observed the previous lectures and all, you might have seen that for the critical flow to occur for a given discharge, it is for a given discharge in a channel, specific energy should be minimum. This is one criteria for critical flow to occur. The next thing is that specific force should be minimum. Just now we have seen that. You also have seen following relationship: velocity head, that is v squared by 2 g. This should be equal to half of hydraulic depth. You have also seen Froude number should be or you have also seen the following relationship: q squared T by g a cube in the critical flow condition should be 1. This also you have seen, or you can also suggest that in critical flow, for a critical flow, the discharge is maximum for a given specific energy value. This also we have proved, right? That is, for a given discharge, specific energy should be minimum, and for a given specific energy value, the critical flow occurs when the discharge is maximum. That also we have observed that. So, these are some of the criterion for understanding the critical flow, or means to observe the critical flow. These are the essential things required. So, then how will you compute the critical flow? If you see that critical flow, for critical flow in any arbitrary channel section, whether it be this relationship, whether it be this relationship where d is your hydraulic depth, the critical flow depends on the area of cross section. It depends on the area of cross section. It depends on the depth of, or area itself is function of depth. So, there is no need to specify much on that. You can suggest that all these quantities determine whether a section allows a critical flow, means whether the flow in a section is critical or not. These things are dependent. So, once you can identify these parameters, you can easily understand how the critical flow occurs. So, critical flow depends on your area of cross section, hydraulic depth, top width, as we discussed. You can suggest that for any given critical flow condition or for any prismatic channel, say prismatic channel whose cross section is uniform throughout the reach of the channel, then for that prismatic channel your critical depth will be same, isn't it? Critical depth will not be changing for prismatic channels. The critical depth will be same throughout the reach of the channel. And also, suppose in the prismatic channel, in such a prismatic channel, if for the entire duration, if the depth of flow is maintaining the critical depth in the entire reach, that is, this is a prismatic channel, if the depth of flow is critical, then you can suggest that the entire reach of the channel is observing critical flow. The entire reach of the channel is observing critical flow. Why the term critical is being called? If you try to observe that the critical flow conditions and all, especially observing your energy depth curves and all, if you observe the energy depth curves and all, you will see that at the critical section or where the specific energy is minimum, here your curve is almost vertical. At this location it is almost vertical. So, even if there is a small change in energy, that gives you considerable difference in depth of flow, say here and here, gives you considerable change in depth of flow. If this was critical depth, then it shuffles between the alternate depths, that is the supercritical depth and the subcritical depth. It will just alternate in between. That causes wavy nature in the fluid, and the flow in the critical condition, it is mostly unstable in nature, because due to this fluctuation, even a small variation in energy itself gives you considerable difference in height and all that. So, therefore, wavy nature is present, and therefore, it is generally called critical flow. So, critical flow, it is not a desirable condition. If in any channel, if critical flow is existing, it is not a desirable condition, because it will be in an unstable condition and it will not be in a friendly matter if you want to do navigation or if you want to do fishing or you do not want to do any particular things and all, it will be quite difficult. The slope of the channel, say in that prismatic, in the same prismatic channel, the slope of the channel that maintains critical flow, you can describe it as SC. For example, slope of the channel that allows you the critical flow in that prismatic channel, let us consider it as SC. Then, if any slope is given for a similar type of channel and if that slope S is less than SC, the flow will be subcritical in that channel and that type of slope is called mild slope. If any given slope of a channel is greater than the critical slope, if it is greater than critical slope, that gives you supercritical flow. That is quite obvious, right? The depth of flow decreases, velocity of flow increases in supercritical. So, and this is called steep slope channels. So, in open channel hydraulics and all, you will now here onwards here you will hear such terms called mild slope channels, steep slope channels and all. So, this is the meaning of that. So, for computing critical flow, you can devise two parameters based on your various criteria, various discussions as we held. You can devise two parameters. First one is section factor as Z, then second one is hydraulic exponent for critical flow usually given as symbol M. We will discuss on this thing. What is section factor? What is section factor? Section factor Z, this is defined as the product of the area of your water flow, area of the water flow into the square root of the hydraulic depth of that section. This is how the section factor has been defined. So, why the section factor is defined and why you how it is useful in computing critical flow? Let us see into that. If you recall, for critical flow, for your critical flow, your velocity head is equal to half of the hydraulic depth d. If this is the case, you can suggest that V is equal to Q by A. So, that gives you Q squared by 2 G A squared is equal to d by 2, or rearrange the terms here. What will you get? Q squared by G is equal to A squared d, or subsequently Q by root G is equal to A root d. So, A root d we have already suggested that this is your section factor Z. So, section factor is, you can either means it is the property of section, this is gives you the property of section, and you can also compute the section factor using the external parameter q. Q is the given external parameter discharged through a section. Mostly in the open channel we are considering q as a constant value. So, therefore, if q is given at any reach, if q is given to you, you can now easily compute the section factor, or section factor is this quantity q by root g, that can be now identified. So, this section factor is for the critical flow. Please note that it is for the critical flow. So, section factor, it is function of depth of flow, right, because both A as well as your hydraulic depth d, they are function of depth of flow. Z is available only in, means this is computed using this relationship. This relationship has been obtained only for the critical flow conditions. This relationship has been obtained only for critical flow conditions. Therefore, Z, whatever Z you compute in a channel section, that will give you the corresponding critical depth at that section, right. So, how will you do that? Because one value of Z will yield you only one type of critical depth in that channel section. In a channel section, for a given discharge, you cannot have multiple critical depths. For a given discharge, there will be only one critical depth in a channel section, that can be easily identified from this criteria as well. We will just go through that. Z, the same relationship Z is equal to q by root g. Once you compute that, once you compute say in a channel section, if q is given to you, if discharge q is given to you, now you can compute Z is equal to q by root g. So, whatever magnitude you get for Z, you now try to interpret that Z is equal to a root d. So, if you know the relationship of d with y, a with y and all, substitute it here. So, from here you will get y, what is the y, and this is nothing but the critical depth y, right. So, this is how you can interpret critical depth from a given discharge. This is one method. So, we will tell you how Z, say Z if it is computed, then we can make it into a non-dimensional form. Based on the cross section, you can obtain a non-dimensionalized Z, you can obtain a non-dimension of depth of flow. If you can obtain them using some characteristic length or characteristic height and all, you obtain the non-dimensional depth. Then Z versus y, if you can plot, from that graph you can easily identify the critical flow. We will just see after this lecture, means in the concluding part of this lecture or today's lecture, we will just explain them in a better way. The next parameter which we suggested is hydraulic exponent for critical flow. So, your Z section factor A is Z is equal to A into root of D. A is function of y, D is function of y. You can interpret now the section factor Z square. You can interpret section factor in such a way that z squared is equal to some coefficient c into y to the power of m. Can you understand that? We are just interpreting them. Now, that is we are defining that as z is function of a is function of y, d is function of y. Here you know this may be function of even multiple powers of y, this may be function of y, or it may be some power of y. So, finally, we can suggest z squared is equal to c into y to the power of m as type of fitting, a type of fitting your section factor in the following form. So, if we can define it in the following form, here m is defined as the hydraulic exponent for critical flow. Hydraulic exponent for critical flow. Okay. So, once you can obtain that, the motive of discussing hydraulic exponent is that once you can obtain m, you can easily identify the critical flow wherever it occurs. Say C is your coefficient, m as we discussed is the thing hydraulic exponent. So, here if I take this is nothing but, if you take the natural logarithm, you will get this thing in the following form, or you can see this thing this is equal to half of log c plus m by 2 log y, or you know what is log y, natural m by 2 y. If I can write it in this form, z is equal to a into root of d, this is equal to a into root of a by t, right. So, what will be the natural logarithm of z then? What will be the natural logarithm of z? You can just try to interpret them. If I take the derivative of this equation d by dy of log z, this is equal to the derivative of this quantity gets cancelled. So, you will get please beg me pardon, here this is m by 2 log y. Once you take the derivative, you are getting it as m by 2 y, right. So, this quantity, once you get this relationship, you incorporate the following quantities here, that is z is equal to a into root of a by t, and try to derivate that. You will see that this is nothing but d by dy of logarithm of a root of a by t is equal to (3 by 2 log a minus d by dy of 1 by 2 log t, or this is equal to 3 t by 2 a minus 1 by twice t dt by dy. Okay. So, substitute this quantity in the LHS here. M by 2y, you will get the following relationship. Your hydraulic exponent m is equal to y, you can take a out, y by a, 3 t minus a by t dt by dy. Right. So, once you get this relationship for any given cross sectional area, you can compute the hydraulic exponent coefficient, hydraulic exponent m. This is equal to y by a 3 into 3 t minus a by t dt by dy. Now, you can easily plot m versus y. M is a non-dimensional parameter. You can easily now plot y with something, some characteristic depth y by b, some non-dimensional characteristic value. You can easily plot the curve, because we already know that these relationship or the section factor and all, you are incorporating it only in the critical flow condition. So, your section factor z is equal to a into root of d. This is also equal to given q by root of g. Consider an arbitrary trapezoidal cross sectional channel. Its side slopes say 1 is to m, let it be 1 is to m. Then how will you compute whether the flow is critical or not, or how will you compute the critical flow in such a channel? How can you compute them? Let us see now. So, trapezoidal channel. So, your A is equal to, now this can be given as B plus m y into y, right, because the depth of flow is y. Your top width t is equal to b plus 2 m y. So, now you can easily calculate d, this is equal to a by t. Once you calculate d, you can compute z, z is equal to a root d. You have initially computed z is equal to q by root g, you will compare, means both are same. So, then it is critical flow, right. So, because for critical flow, this is the relationship, this relationship and all we have obtained, this especially this relationship we have obtained using critical flow condition. We will just see here for an example. In an example, sorry, not an example, let us consider beginning a rectangular channel. That is, in the trapezoidal channel, your m is equal to 0. Area is b y, top width is equal to b, hydraulic depth is equal to y. Okay. So, your z is equal to a into root d, like this you will be, how will you compute them? You now know that z has the dimensions of L squared into L to the power of half, that is L to the power of 5 by 2. So, in our previous part we have suggested that we have to use non-dimensional Z versus non-dimensional depth y. This we have mentioned it earlier. So, how will you make this Z as a non-dimensional form? Here this Z is now, if you see for any trapezoidal channel, the fixed parameter is your width of the bottom width of the trapezoidal channel B. It is a characteristic length then. So, if you make say Z by B to the power of 5 by 2, if you obtain a parameter, if you obtain this thing, then now you can easily form a chart, a series of data for different this thing. Similarly, the non-dimensional form of depth is given as y by b. Okay. So, any graph can now be plotted versus y by b versus z by b to the power of 5 by 2 for a trapezoidal channel. So, your z b to the power of 5 by 2 for a rectangular channel, this is nothing but if you rearrange the terms here, it will come to be y by b whole to the power of 3 by 2. Why I am giving this relationship here is that we will be discussing a particular graph using this relationship now. What happens, say for m is equal to 1 trapezoidal channel, in a trapezoidal channel, if m is equal to 1, the side slope is 1:1, then you will have your area of cross section is equal to A is equal to B plus y into y, your top width T is equal to B plus 2 y, your hydraulic depth D is equal to B plus y into y by B plus 2 y. Subsequently, you can compute z is equal to a root d. You will see that your non-dimensional relationship z by b to the power of 5 by 2. This is nothing but y by b to the power of 3 by 2 into 1 plus y by b to the power of 3 by 2 by okay. So, you are now getting the following relationship. This quantity now we will be discussing in the following graph. So, for a rectangular channel, you can have different ranges of y by b ratios and the corresponding section factor in the non-dimensional form that has been computed here using the formula which we derived it here, that is computed here. Similarly, for a trapezoidal channel of side slope 1:1, for different values of y by b ratios, what are the corresponding non-dimensional form of the section factor, that is also computed here. They can be easily plotted in a logarithmic channel as shown here. So, if we can plot the channels for different sections now, in similar way, you will get different type of curves. These curves, you can give this as a standard curves. Whatever section factor or whatever discharge is available to you now, or whatever based on your discharge in a section, now you can easily identify what will be the corresponding critical depth. For example, if in a particular channel or for a trapezoidal channel of side slope 1, you got a section factor value somewhere here, if you got somewhere here, then just go and interpolate that, find that what is the corresponding non-dimensional depth, whatever is there here 2, 3, between 3 and 4, that is 3.5 or 3.6, what 3.4, let us say 3.4. So, in this case 3.4 is the non-dimensional depth that can be now easily interpreted according to your requirement. So, this will give you the critical flow for the given, say z is equal to q by root g. You are first computing it for a cross sectional channel, because q is a given parameter, q by root of g you are computing it. Using this you are trying to identify, means this you will subsequently obtain z by b to the power of 5 by 2, because b is also a given parameter. You have identified that that value is occurring somewhere here. Now, you are trying to interpret the corresponding y by b. So, you got y by b value as 3.4 in this particular case. Interpret what will be the critical depth. So, y critical depth will be y is equal to b into 3.4, that is all. That is how you compute critical flow using the charts. Now, for the same, the hydraulic exponent m, you have suggested that m is equal to y by a 3 t minus a by t dt by dy. For the same trapezoidal section of 1:1 side slope, you can now easily compute m. M is equal to y by thrice b plus 2 y minus b plus y into y by b plus 2 y, and dt by dy for 1:1 side slope, dt by dy is equal to 2. So, that 2 has to be multiplied here. You can subsequently rearrange the terms in a non-dimensional form. Here if you, so you will get m related to something with y by b to the power of some quantity. You will get such a relationship. Even this can be plotted as we have plotted non-dimensional section factor versus non-dimensional depth. Similarly, you can plot hydraulic exponent versus non-dimensional depth like this. That curve also will yield you how to identify the critical flow. We will just quickly go through an example to compute critical flow. Given discharge 6 meter cube per second, you are given a discharge q is equal to 6 meter cube per second. Bottom width b is equal to 2.5 meters. You are now requested, say if it is a rectangular channel, what is the critical depth, if it is a trapezoidal channel of side slope 1:1, what is the critical flow depth? You are now requested to find that. We are now following the algebraic method first. Before using the curves whichever we have utilized or whichever we have derived, before utilizing them, let us go through the algebraic method to compute the critical flow, because this is a rectangular channel, quite easier one. This is the criteria for critical flow. Substitute the quantities here. You will get 6 squared into T is here, breadth itself 2.5, G 9.81 into what is your A? This is 2.5 cube into y cube. This is equal to 1. From this equation, you will get y, that is your critical depth y c is equal to 0.837 meters. From this relationship, you will get that. For your trapezoidal channel, you can use the trial and error method, the same formula q square T by G A cube is equal to 1. Substitute the quantities, 6 squared into 2.5 plus 2 y c by 9.81 into y c cube into 2.5 plus y c whole cube is equal to 1. Rearrange the terms, you will get some relationship. You have to use trial and error method, you can use that to solve this equation. You can use the trial and error method to solve this thing. I have used a trial and error method. Through several iterations, I obtained around 0.755 meters. Suppose if you are getting something different, you please let me know that. Maybe your approach may be better, or your hit and trial method may be better compared to mine. This is how you solve or you compute critical flow depth using algebraic method. In the next class, we will discuss for the same thing using the charts whichever we have shown it here. You will discuss them, how to use them and compute the critical flow. Thank you.